I welcome all of you to the video lecture series on fluid mechanics. This lecture is on topic 1 on introduction. The title of this lecture 4 is classification of fluid flows. In nature as well as for various industrial applications, we find various types of fluid flows. Their classification is presented here. Based on the role of viscous force in a flow region, there are two types of flow regions: viscous flow region and inviscid flow region. More will be discussed little later. Based on the configuration of the fluid flow always occur in certain geometry. As I had mentioned in the definition of fluid mechanics, that in fluid mechanics we study the flow which is generated due to interaction of a fluid with a solid surface. So there is always a configuration of a fluid flow along with the solid geometry. So based on the configuration, there are two types of flow: external flow and an internal. Based on the variation of density in a fluid flow, we have two types of flow: compressible flow, where density is varying with space as well as time; incompressible flow, where in the flow region the density is uniform, almost uniform. Based on the orderness of the flow, at smaller flow velocities, it is found that the flow has certain order, smoothness, whereas when the flow velocities increases after a certain value, there it is found that the flow becomes disordered, it starts fluctuating, and there is a chaoticness in the flow. So based on the orderness of the flow, these are the two types of flow: laminar flow at low velocities and turbulent flow at larger velocities. Whenever there is a fluid flow, depending on whether we need an energy to get that fluid flow, then it's a force flow. Whereas many times under natural condition also, like if an object is heated, buoyancy naturally comes into this problem and you have a buoyancy induced natural flow. Whereas for force flow, we need pump or blower to generate the flow. For most of the fluid mechanics problem, initially when the flow starts, there is some transient. However, finally the flow reaches to a state where you get a flow picture of the fluid flow, which stops changing with time. This is called as steady flow. Whereas if at later time instant the flow reaches to an unsteady state, then we have an unsteady flow. Depending on whether the flow properties variation in space, there are three types of fluid flow: one-dimensional fluid flow, two-dimensional fluid flow, and three-dimensional fluid flow, where the flow properties are varying with respect to one space coordinate, two space coordinate, or three space coordinate respectively. Now I'll present each of this classification separately with the help of some example problems. The first classification which was presented is the viscous and inviscid regions in the flow. So as I mentioned, that this is based on the region's role of the viscous force. Like if you consider the example problem as shown here, it's a flow across a stationary plate. This is a stationary plate and the fluid is flowing from left to right. If this plate is stationary, you have according to the no-slip boundary condition, the fluid which comes into contact with this plate has a velocity of 0. Very far away, the velocity is equal to the free stream velocity which is at the inlet. But near to the wall, due to a thermophysical property, dynamic viscosity, which is due to the stickiness between the different layers of the fluid, there is a velocity gradient which sets up. And due to this velocity gradients, in this flow region, if you take the product of the velocity gradient with the dynamic viscosity, then you get what we call as viscous stresses. And so in this region, in this flow region, the viscous stresses or viscous forces are large enough. However, if you move away, this is what is shown as the boundary layer, outside which the velocity gradients are negligible, and the viscous stresses are also negligible. So outside this boundary layer, you have an inviscid flow region where the viscous forces are close to zero, whereas near to the wall, you have a viscous region. Now, the purpose of doing this classification is that historically, getting a solution for getting an analytical solution for the complete viscous and inviscid flow region mathematically, analytically is not possible. What has been possible is that in the inviscid flow region, analytical solution was proposed, and so this solution is possible in the inviscid flow region. Fully analytical solution for the general class of fluid mechanics problem is not possible in the viscous region. So that was the reason that it was classified into these two types of flow regions. Whereas when you do an experiment, you can get results both in the viscous and inviscid regions. If you do in computations, you can get accurate results both in the viscous and inviscid flow regions. But note that complete analytical solution for a general fluid mechanics problem is possible only in the inviscid flow region. Depending on the configuration of the fluid flow along with the solid across which it is flowing, there are two types of flow: external flow or an internal flow. Like if you consider flow across an aeroplane or flow across a circular cylinder as shown here, then in this case, this is called as an external flow. Whereas if it's a flow in a pipe or plane channel, then it is an internal flow. The fluid, note that the fluid is flowing external to this surface. In this case, the fluid is flowing inside a pipe, which is, these are the solid surfaces of the pipe or a channel. So the flow is internal to a pipe. Here it is external to an object. That's why they are called as external and internal flow. The point to note in this classification is, in an external flow, the boundary layer, the region in which you have a large velocity gradients, is free to develop without any constraint being imposed. Whereas in case of internal flow, you can see that for flow in a pipe or flow in a channel, this is the growth of the boundary layer. But the boundary layer not only grows from the bottom wall, the boundary layer also grows from the top wall. So this growth of the boundary layer from the bottom wall is constrained by the growth of the boundary layer from the other wall. Okay, so this is called as an internal flow. However, we many times observe a problem which has a characteristics of both external and internal flow, such as this problem. Like if this circular solid object is placed inside a pipe or a channel, then this problem has characteristics of both external flow and an internal flow. Note that the characteristics of an external flow is flow separation. Okay, and the characteristics of internal flow is boundary layer interactions from the two walls. So both this phenomena, the characteristics of the external and internal flow, is observed in this problem in flow across a cylinder in a pipe or a channel. So it has the characteristics of both external and internal flow. This is the third in the list of classification of the flows: compressible versus incompressible flow. At 1 atmospheric pressure, 1% change in density is caused by 210 atmosphere of change in pressure for a liquid, and by only 0.01 atmosphere of pressure change in gases. So you can see that if you have a flow region consisting of a liquid versus a flow region consisting of gases, for 1% change in density in liquid, you need a very large change in pressure in the flow region with liquid, that is around 210 atmosphere. Whereas in a gas flow region, only if in the gas flow region, if there is change in pressure by 0.01 atmosphere, it causes a 1% change in density. So with this statement, I just wanted to demonstrate that for liquid, the most of the time, the change in pressure we observe in the flow region are much less than this 210 atmosphere, and the density variation in liquid for all practical purposes is considered it to be incompressible. The density is not varying with space. Whereas for gases, if the velocity in the flow domain is very large at high speed gas flow, it is found that the density variation in the flow region is large enough, and in those cases we consider the density variation. However, at low speed gas flows, we still consider the density variations as negligible. So there is a parameter which basically demarcates the low speed gas flows which we consider as incompressible versus high speed gas flow which we consider as compressible. The parameter is called as Mach number. It is defined as the ratio of the velocity in the flow region divided by the velocity of the sound in the fluid. And it has been found that if the Mach number is less than 0.3, then so let us say in air, the speed of sound is 346 meters per second. And if you take 30% of that, the velocity comes out to be around 100 meters per second. So air, if the flow velocity is less than 100 meters per second, then it is found that the density variation in the air flow region is less than 5% in the whole flow region. So we consider it to be incompressible. So this is the demarcating velocity in the flow region for air. So you can see that in air, if the velocity of the flow is less than 360 km per hour. So for example, if you are considering if a car is moving with a velocity less than 360 km per hour, which is extremely large, especially for a car. So for all practical purposes, we consider the flow across a car as an incompressible flow. However, if you consider an aircraft which is moving at much larger velocities, then for such cases we call those as high speed gas flows, and for which we consider the density variation. So the fluid mechanics which is involved for negligible density variation in space is called as incompressible fluid mechanics, versus for if you consider density variation, then we call it as a compressible fluid. This course is mostly on incompressible fluid. The next classification is laminar versus turbulent flow. So in a fluid flow, let us consider at low speed flows, the fluid has certain orderliness. However, if you keep increasing the flow velocities, there is some disorderliness or unsteadiness which sets into the flow, and at larger velocities, the flow transits from a laminar flow to a turbulent flow. Now, the characteristics of the laminar and turbulent flow will be presented. In a laminar flow, there is certain smoothness in the flow, orderness, and the flow is layered. Whereas in a turbulent flow, the flows is fluctuating, disorder, and chaotic. Laminar flow is, if a particle is moving in a particular layer, laminar flow is also called as a flow in a laminae, where a fluid particles stay in a layer without moving to the adjacent layers. Let us consider as a fully developed flow in a pipe as an example. These are the surface of the pipe, and this is the fully developed velocity profile for a laminar flow. So in a laminar flow, if a fluid particle is in a particular layer, it stays in that layer, and the fluid particle doesn't move to the upper and lower layer. Whereas at a larger flow velocities, the fluid, when it transits from laminar to turbulent flow, the fluid which is having a horizontal velocity, now it starts having a vertical velocity fluctuation, whose time averaged value is equal to 0. So at certain time instant, let us suppose it's a v velocity, vertical velocity is a v velocity. When v is positive, the upward velocity, the velocity is up. This fluid particles move upward, and when this fluid particle moves in the upward layer, which is moving with a larger momentum, then it tries to slow down the momentum of the upper layer. Whereas at certain other time instant, where this v velocity is negative, this fluid particles moves downward, and it tries to accelerate the bottom layer. So this v velocity fluctuations leads to a mixing of the momentum in the vertical direction. And if you consider if let us suppose this flow velocity for laminar is close to the transition, then for a turbulent flow, for almost same mass flow rate, you get a velocity profile which is much flatter. So you can see that the momentum transport in the vertical direction, streamwise momentum transport in the vertical direction in a turbulent flow leads to a mixing of momentum, and it leads to a smooth velocity, a much flatter velocity profile for a turbulent flow. The next classification is based on the energy required to create the flow. This is a natural flow where we do not need any external energy source to generate the flow. Let us suppose you consider a heated object as shown here. Then the fluid which is near to this heated object gets heated up, it becomes lighter, and then it tries to move in the upward direction. So for a heated object, you get an upward flow. Whereas for a cold, if you have a cold object, then the fluid nearby gets cooled, it becomes denser, and it tries to move in the downward direction. This upward and downward flows are buoyancy induced flow. They are the natural flows. Whereas if you have situations where you need the external energy source, like if you need a pump to basically generate a flow for liquid, and we use blower to generate flow for gases. So for such flows, we are called as forced. This is the classification of flow with respect to, if we consider the variation of flow with respect to time, steady versus unsteady flow. Let us say if you consider flow in a pipe, and initially let us say the fluid is stationary in a pipe. However, as soon as you switch on the pump, the flow gets initiated at the inlet of the pipe, and if you create a movie for flow, velocity distribution, pressure distribution, as soon as you switch on the pump, the flow, there is a variation with respect to time, and those time-wise variation are called as flow transients. However, for flow in a pipe, at much larger time instants, at larger time durations, you find as time progresses, finally the flow reaches to a state which is called a steady state, where in a fluid dynamic movie the picture stops changing. However, there are certain other class of flows which reaches to an unsteady flow. Like in previous lecture, I had shown you that for flow in a flow across a cylinder, at low Reynolds number, at low flow velocities, you get a steady flow where you have a twin recirculating flow region. However, at Reynolds number greater than 47, I had shown you get a vortex shading phenomena, which is a periodic flow. In a periodic flow, you create a fluid dynamic movie. There will be an initial transient, but finally, instead of reaching to a steady state, it reached to a state which is called as periodic state, where in a fluid dynamic movie, a fluid dynamic picture repeats after certain time duration, which corresponds to the time period of vortex shading. Periodic flow is one of the case of an unsteady flow. There are other cases of unsteady flow like quasi-periodic or a chaotic flow. After this flow classification based on the time-wise variation, the next classification is on the spatial variation, which we call as one-dimensional, two-dimensional, three-dimensional. So in a flow region, based on the flow properties, velocities, pressures, and temperature, if they are function of one spatial coordinate, as shown here, they are called as one-dimensional flow. If they are function of two, then two-dimensional. If they are function of three spatial coordinates, then three-dimensional. This is an example of flow in a pipe, where once the flow becomes fully developed, the velocity does not vary along the z and along the azimuthal direction. It varies only along the angular direction. So you can see u is shown here as u is the horizontal velocity or axial velocity for flow in a pipe. It's a function only of the radial coordinate, not a function of theta and z. This is a one-dimensional flow for a fully developed flow in a pipe. If you consider flow across a cylinder, earlier I had shown you the transition from steady to unsteady flow. Here I am discussing the transition from a two-dimensional flow to a three-dimensional flow. So here it is shown that for a two-dimensional flow, if you take two planes in the axial direction, you see that at Reynolds number less than 160, the velocity pressure distribution, the flow properties in this plane and in this plane at a particular time instant is same. So if you take any plane along the axial direction, transverse plane along the axial direction, in all the planes at Reynolds number less than 160, the flow pattern is exactly same. This is the case of two-dimensional flow. However, at larger flow velocity, when the Reynolds number is greater than 160, it is found that the flow pattern or the picture of fluid dynamic movie in this plane and all the planes in this axial direction, they are different. So this corresponds to a three-dimensional. So the classification, these are the list of classification which I discussed in detail through whiteboard presentation. So with this, I had come to the end of this lecture. These are some of the reference book for this topic. Thank you for your attention.